And wait. Okay. So in today's talk, I'm going to basically introduce my work on the fixed body systems in the finite volume system. So and especially their application to nuclear reaction theories. So the outline of my talk, one second, is the following. First, I'm going to introduce to you guys about the finite volume method, which is apparently mostly used in the QCD sectors and not so much about the nuclear theories. And then I'm going to do some introduction of my work, mostly about the long-range forces, as well as another new methods to do complex scaling of finite volume. So in the end, I'm going to introduce you with a preliminary idea about the finite volume and the asymmetric continuation. So the question we need to ask always is why we do finite volume. So in many simulations, we do a simulation on the box. So say if we want to simulate a kite, we put the kite on the periodic box and do the simulations. To relate the kite with the kite that's in the real world, we took the kite out of the box in the finite volume method. So suppose my work is given from like a set of data that's varying with the lattice, and I would like to use the finite volume method to extract information that's relevant to the attributed scale. The previous results about finite volume methods are basically twofold. First, they perform essential calculations on the short-range potentials, and the short-range potentials in the finite volume box is regarded as the particles. How does it say about the knowledge about the world and about the interactions around the world? And there are two main categories. The one is for the scattering states, and the other is for the bound states. For the scattering states, it's decaying in the power law, and for the bound states, it's decaying exponentially. And these relations also can be related to the various informations observables. In this case, for the bound states, it's the NC constant, which is going to be related to nuclear reaction theory. And they are also generation to all kinds of different systems. And if you want to know more about this wide subject, you can take a look at the reference here. So the general idea behind these things, we start to think that the perturbation has to the infinite volumes by connecting the infinite volumes with the periodic boundaries. And this tends to work well, but sometimes it doesn't explain a few phenomena. So instead, we just impose quantization conditions with this boundary constraint. So how does this quantization condition work? We have a 1D toy model. The quantization conditions from the box boundary gives these nice equations in the 1Ds and makes this a single 1D lattice into a circle. And if we look at the information on the diagrams, the relation between the phase shift on the 1D by the boundary condition is going to be a straight line, the right line here. And if we have another size of the box, it's going to be exactly another different line with a different slope. So when they meet with the infinite volume phase shift, we have a solution on the finite volumes, which is also an eigenvectors for the corresponding Hamiltonians. In the real life, we're using these relations backwards. We are given a few data points that has eigenstates, and then we use the solve equations to fix the relations and try the relevant parameters in nuclear reactions. So we hope everything should just simply turn from 1D to 3D, but however, the real world is always complicated. Say for this example, we have a nice one, an S wave in the infinite volumes, which preserves the spherical symmetries and the rotation symmetries. But when it goes to the cubic situations, with a period boundary, this nice symmetric 1D symmetric sphere just transforms into a complicated situation. This correspondence is everywhere in the cubic symmetries. For example, for the E1 symmetries, you need to use angular momentum from 0, including zeros, 4, 6, 8, etc., etc. It just doesn't do things like we want. This is causing a fat cosmizing. And not only the S wave is going to contribute to the box, the system, but also all different kind of partial wave can contribute. So what we do here is we expand the boundary, extract the wave functions in terms of some things that are satisfying the boundary conditions, and expand these equations in higher power, higher partial waves. And in doing this, we have a homogeneous linear equations, and we solve this equation here. And this is going to give us the correction due to okay, no man, I just stop using microphone. So yes, I think you can. I can just raise my voice. So basically, it's better without microphone. So basically, for these things, we solve the equations by giving a set of discrete solutions, and which is basically eigenstates, and extract relevant parameters, which is the phi range expansions, thing like that. And there are also other methods, for example, including the beyond single channels. They tend to deal things a different method, but in the end, they got the same quantization condition equations, but it's going to be way more complicated for the case with beyond single channels. And this is a paper that you can go to see how things are complicated in this case. So we certainly don't want to solve a bunch of linear equations. Instead, we want to have some nice relations, just to only have single equations that we can work on. And also solving a bunch of linear equations is also expensive. It can sometimes go as expensive as solving the original system. So in this case, we worked on something around the poles. I'll take a look at the poles, and luckily, in this case, the S-wave, the S matrices is going to be dominated by these poles. And therefore, we can just simply regard the remaining terms, just drop them because they are not important. And this will give us a lot fewer equations, and this is partially useful for bound states. So we have know how to do things on the bound states. Let's now take a step forward and take a look at how to do things with a long-range force. In this case, the long-range force we are include is a repulsive Coulomb interaction that should be very common in the nuclear systems. And to have you a better view, the system in the infinite volume we are considering have two parts, which is the short-range part and the long-range part. And the Coulomb force is described by the 1/r relations with the gamma factor, gamma parameters that describe the strength of the Coulomb interactions. And if you look at the wave functions on the long range, they will just behave like the weighted functions. And this weighted functions is just going to behave like the exponential decays plus times the factor, that's a power law. And in these weighted functions, there's an important parameter, which is eta. This eta is going to be described by the relations of the power law, the gamma factors over the kappa, which is the bending momentum. So to put the Coulomb force in the finite volume box, we implement a simple cut. The issue with the Coulomb force in the finite volumes is if we don't do the simple cut, the tail will cause a huge divergence problems. And this is actually a standard approach in the lattice CFTs, and as well as we now have a complete counterpart in the finite volume of the Hamiltonians corresponding to the infinite volumes. So this Coulomb force we implement also has the nice relations in the lattice QED potentials. For the lattice QED potentials, what we basically do here is we sum all the possible lattice, all the lattice modes, and it's also causing a problem, which is the zero modes, and we remove the real modes because we don't want the problem. And it turned out to be working pretty well in most situations. And also it's a periodic potentials because the basis we construct from is periodic. And it's easy to implement in the calculations. However, we are doing analytical computations, so it's not so much so easy. So we have to look at how this lattice Coulomb potential works by compare expanded analytically. And we find that the leading term is exactly our Coulomb potentials, and plus the constant terms and also some higher power law terms. And this is a picture that's showcasing how we can treat this force perturbatively relative to our Coulomb force. There are also all different kinds of Coulomb force in the nuclear physics. And the general rule for treating this is, in our mind, is just treating these terms perturbatively, and because it has a nice relation to lattice contractions, and we think this is the force to go. Okay, now let's take a look at 1D situations, which things are pretty easy in this setup. In the 1Ds, we can just simply take the boundary conditions techniques and see how that expands around the boundaries. Because we know that in the bound states, everything is pretty much localized, and the terms are dominated by the leading asymmetry systems. Can you explain your boundary condition in the red? Like those boundary conditions. These are just boundary conditions. Suppose we have a bound state, and these boundary conditions just we evaluate the states as the wave functions at the boundaries, and for example, this one. We do the first derivative at r equal to L over 2, and because of the Neumann boundary condition, the periodic things, it just goes 0. And this is the quantization for the 1D. Yeah. So if we do the expansions around these boundaries, we can get the energy shift in these forms, where F is just the exponential here. And we can do the same thing for the weighted function as well. It turned out we can just simply plugging in the same things here as we have done for the non-Coulomb case. It will just go with a little bit complicated, but everything came up nicely. And this theme also works for the half spheres, where the symmetric of the spherical symmetry is still preserved, and it will give some relation like this. Yet this nice theme of the 1D Coulomb box doesn't extend to 3D because the long-range tail of the box, long-range tail of the wave function of the Coulomb force. So we take another step back by using the information that we only need to deal with one channels. So and construct a wave functions with a naive guess from the boundary condition. A natural way of doing making the infinite volume solutions periodic is simply by summing all the shifted copies of the infinite volumes, and we get something which is periodic in this case. It turned out to be a really good approximation to the exact waves, and it's related to the exact wave by a higher power, higher exponential terms. And now we know the approximate form of the wave functions. We can just simply compute the expectation values using these approximations and compare with the infinite volumes, and we get this integral here. And this integral is going to be evaluated and give us the nice power exponential relations. And this seems actually works really nice for all different setups that we don't have the exact information or don't know how to do deal with the boundaries mathematically. And in this case, this approximation also a little bit missed the mark, and we had to include another term. And by using the perturbation theories, the way of dealing this perturbatively is to add the Coulomb force by looking at compare the Coulomb force with the infinite volume ones, and regarding the difference of the finite volumes and the infinite volumes as a perturbative term. And doing this, we get intermediate Hamiltonians. And we use these intermediate Hamiltonians to construct the Lüscher's formalism, and everything just remains the same, except we are using an intermediate Hamiltonians, and we need to perform perturbation theories on it. In principle, this method also works for other long-range terms as well. Suppose we are given a strong magnetic force, which goes 1/r squared. This same also should work. Those subleading terms that bothers us turn out to be solved by this method. The first term is the perturbation corrections, because we are using intermediate Hamiltonians. And this term is just bound by the leading corrections because the energy matrices, the energy and the difference compared to the infinite volume is always positive. And there's also corrections because we are using approximation to the intermediate wave functions. And we also compute these terms numerically and see they are indeed comparably small compared to the leading contributions. And they also gives us a nice power law relation compared to the leading terms. For our results, for the S-wave case, we have really nice relations that we can just simply replace the exponential terms by the weighted function square. And the blue term is the corrections, and we know it behaves as power law terms and should be able to drop if you have a large volume. And this equation reduces nicely to the non-Coulomb case. If the eta goes to 0, this term we have seen before will just vanish. And this term, this weighted function, we just go to the exponential functions as well. And in principle, we can just apply these things to our different configurations by properly dealing with the perturbative corrections to our Coulomb potentials. And this formula, this method should extend easily to Helm angular momenta as well, where the problem is we don't expect a nice relations as simple as this, even for the P-wave case, which should be simple. So, okay, here is some benchmark we run against our model. On the left side, we see we use the lattice setup with the OA3 improved lattice lattice setup, and we gradually increase the Coulomb strings while keeping the bending momenta the same. And we see a strong deviation from the linear case, which is the exponential because we take the log scale here. And as the reference, we have the alpha particles at 0.5. And we see that we also run these continuum calculations and compare with our two-body simulations, lattice simulations, and we see things match up pretty well. And we also run independent lattice setup, which we have a helium-3 and tritons. And these, we see these also fits well. And for this case, where the Coulomb interaction is super small, there's already 5% difference already. And now we are talking about the NCs. The NC parameters are really important parameter that's used to extract try to calculate the reaction rates in the astrophysical environment. And the ways of doing trying to emulate NCs are trying to compute NCs from nuclear theories is basically two categories. One is the phenomenological approaches, and the other is ab initios that we can extract probability densities. And not until before recently, we have developed our methods that can use to do this ANC extractions from the finite volume data. The phenomenological approaches relies on the reaction data, and for example, they use R matrices and figuring out the poles and resonance. And this is a review paper that talks about how to do this for the alpha and carbon-12 capture reactions. And for the probability densities, I know a little bit more. And in the first principle calculation, the probability densities method is facing some important challenges. These are three major ones. The first one is some methods does not produce the tail. For example, the short models, they are using the Gaussian tails. They have the Gaussian tails, and well, in our case, we are expecting a exponentially decaying tails. So the solution to that is we match the tails by considering the inner part that's not going to change much, and the tail part that we are using the same method as a R matrices method. Yeah, that's probably a green function. Yeah, and for this case, on the picture shown here, we see another two major challenges, which is the ab initio in simulations doesn't really replicate the energy level structures. It's always hard to do the nuclear structures on the ab initios, and we now need to rely on this not so useful information to extract NCs. And the solution to that is we simply use the information from the experiment.
Can you explain to these people like what that part, what the plot really means?
Yes, I'm going to do that. Yeah, okay, sure. In details for this plot, we are seeing here. Okay, we are seeing here is these are the breakup. They just what they do here is they suppose you have a cluster of lithium-8, and you just extract the neutrons away from these clusters and compute the probability of the wave functions when you have another neutron away from the center of the mass. And they get these net curves, and you see that it's hard to replicate the tails. They are noisy. We're having some problems sampling the tails, as well as we need to use the small change in the energy levels, which is the theoretical value, which is the pH, and the experimental value is the experimental. It gave a huge difference in this case.
But don't you think that you have a wrong analytic behavior?
What?
Don't you think that you have a wrong analytic behavior?
What?
In the tail?
Just weaker functions. Just a weaker function.
Okay.
It's almost.
Yeah, you're asking about tail behavior, right? Yeah, these tails are should be just like the wave functions that I introduced in the beginning of the sessions. That if you take the infinite volume limit, they just do the wave functions, and which is a function that's just like exponential terms divided by the power terms, which the power terms is related to the Coulomb stress.
Right, but one seems to be curving up and the other curving down. This one.
It's curving up.
I mean, the numerical results seem to be curving down.
I think this is mostly, the thing they mentioned that they do not produce the tail right correctly, and also they are having a hard time sampling the tail right.
Like, I think this is maybe also true for lattice. Do you have a sense of why it's so hard to get a tail right?
For the lattice effect, I think actually it's a little bit better because we still have the exponential tail, but it's just noise. It's just noisy. It's roughly exponential, but noisy.
It's energy driven, right? It's all about energy driven. So the tail doesn't give you much change in the energy. So it's very hard to get that.
Yeah. If you mean the mixed energies, if we by chance make the energy to be exactly the same, they would behave really well. But if by any chance it's missed like by a few MeVs, it's going to miss really much. This is what happened basically. So for our case, I'm showcasing a helium-4 and simple calculations as done on the many-body frameworks. And we see that in this range is working really well until the error terms emerges. And the reason we do this is there are two major reasons we do this. First, it has a better error performance because we have pretty much many ways to extract energies from the many-body theories. And also the energy is something that's really easy to compute compared to other operators, and still we need a correct breakup energy. In this case, the helium-4 is something that we can just get really accurate breakup, but for the case when you go to more than this, for example, the oxygen 16s, thing like that, the breakup energy is going to also miss, even in our case. And we also don't see from the picture that we don't have pretty much data points to vary the lattice and while keeping the accuracy under control. Another major challenge we're facing to extract.
Actually about lattice challenge.
Sure.
What is the reason for error exploding?
This is a log scale.
But error become bigger and bigger for larger.
We're calculating the delta E, which is the energy. We're just calculating the energy shift, and in this case, when we have a larger box, energy shift just becomes small, and we put on the log scales, and here, it's just like the previous ones. They're also doing the log scales.
Sure.
And the log scale, if you compute the error compared to that, even a small error can be, if you have 1 and 1, 1 plus or minus 1, the log scale is going to give you a huge error downside because the other part is almost 0, right? It's just doing the.
You're saying like for large L calculation, your absolute error actually is not bigger.
It's not bigger. It's the same error, but on the log scale, it's just more apparent. And we need a small difference. We need an accurate small difference to extract information. And that's because of the difference is comparable to the small errors here. It's not much useful. We don't really know which one of the error part is the correct error part. Another problem appears from this calculation is that we found the cluster structure to be much more complicated than we had imagined before. So for the simple case, we treat the clusters as point-like particles, and we will get the same results as what we have for the simple finite volume case. But for the cluster calculations, we find that this bending momenta, although the energy shift is not changing much, even in the lattice setup, the bending momenta, because it needs several compared to the smaller clusters, and it's actually at the range of the energy shift. So that is going to somehow interfere with our assumption that we don't have the bending momenta is not away from the poles. And we need to include that terms, which is the kappa away from a little bit away from the poles, and see how the terms with that goes. And also there are multiple different breakup channels that could also severely impact our results. And as a summary, we have development methods on how to calculate the energy shift using this long-range force, and we also see how this remaining part of terms changes. And we also trying to apply this theme to the ANC calculations, and we found some problems that's related to clusters. We want to see if we can improve this classical configuration in the futures. And what matters most is that we have more data. These problems are not going to be a big challenge anymore. So we need to see if we want to see if there are any problems, any method that can give us more data points. So the complex scaling we are working on, is actually might be a solution to these complicated problems of finite volume spectrum. We came up with a new idea that's doing the complex scaling inside this finite volume box. The complex scaling in the finite volume box is just like what we do for all different lattices. We just put another scaling on the lattice, but in this time it's a complex scaling factors. And because we actually put everything, the scale factors in the mass, And in this special case, we get some sort of complex mass, which is nothing new, but it is what it is. The potential in the complex scaling need a special care, where, for example, if we have a Gaussian potentials, the complex scaling, if we have a large complex scale angles, this scaling angle is going to make the potential actually diverging. So there is a upper limit that the complex scaling can do to extract resonance. And also, in our case, we are actually working with the period boundary conditions. We need to preserve the period boundary conditions to make everything work. This is what it looks like when we have finite Hamiltonian, finite volume Hamiltonians with complex scaling. The method we use here first is, the previous method, we have the shifted sum of approximations, actually works pretty good in this case. And the tricky part is how to compute the expectation values via the C product, which is the thing you have to do on complex scaling to make everything right. And the final results, the results we get from this method looks like just scale the L's by complex scaling factors. And the problem with this method is it only gives leading terms, and it can be oscillatories and also can be shallowly localized for the resonance states. Both reasons require us to think about what's going on when you expand beyond the leading terms. When you expand beyond leading terms, the previous method is not working so well. We had to use the lattice green functions and compile, and we found that these lattice green functions on the complex seam actually have a nice relations with the normal seams, where we haven't done the complex scaling, and by just shift the E and the energies we are working on to a zeta square, which is the complex scaling factor.
Not the exponential then extra factor in exponential.
The exponential doesn't have an extra.
Okay, so P and
yeah, because P is rotates to the conjugate of the R, and they just cancel out. And this is important because if you don't do this, it's basically you break the period boundary condition. If you have only one factor, and the periodic series is going to be broken by if you simply rotate the 1 over n's, and it doesn't become the same. It doesn't preserve the periodicities, and okay, so we know the green functions. We can just use the previous knowledge because it's around the poles, and expand the quantization condition around the poles and get less subleading terms. And the results we have here showing what's the subleading terms before the second power law, which these terms include the terms which is away from the residues. And these are the terms that need a new parameter. And we have seen the two terms emerged in this case, and the same method. In principle, we work for higher partial wave. The P, for example, the P wave will have a sign chain from the positives and negatives. And for L bigger than 1, the higher partial waves, the subleading term, we think we just need to know how to expand the Lüscher zeta function correctly, which is another mathematical challenge. And here we just showcase how this complex scaling can help in the bound state calculations. In the bound state calculations, because we have another parameter, which is now parameterized by the complex rotation angle phi, and we see that instead of varying the lattice, we can simply change the phi angle and get a nice finite volume correction terms. And we fit these terms, and this is also going to give us an ANCs. The trouble part, the difficulty part about this is how to do complex scaling correctly on the lattice. And that's another subject. And we also run another benchmark where we had two resonance. We have one resonance, which is a S-wave resonance, which is localized at around, located at around 1.6 plus or minus 0.4 6, and this is this phi angle. We change the phi angle, and we find that the leading term also works really well. But there's a need to include the subleading terms. Yes, this is a 2-body systems, and yeah, we have done some calculation on the 3 bodies, but the 3-body duration, you have to do another duration for the pure 3 bodies. It's not going to be the same as 2 bodies, and they have to be worked out again from the beginning.
I think that phi, so the correct converge result corresponds to larger phi.
Which one?
So if you look at resonances, it's the larger phi's that correspond to the physical value. I'm trying to see the converge. So we're saying like
if you have a large, just suppose you have a resonance located at a Riemann sheet, and the larger the phi angle is, the more localized the resonance is if you rotate rotates the contour.
So you believe numerically the branch target rotate further away.
Yes, further away, and you have a much closer to the physicals.
Okay, so what about the left side?
Left side?
Yeah.
This is the bound states.
So the bound state shouldn't depend on phi.
The bound state actually depend on phi because we're putting things in the finite volume. The things are changing because there's a finite volume corrections, and the pole is still out there, but because of finite volume corrections, there's a correction to the poles, and that correction is depending on the phi angle. It's a correction that depends on the phi angle. There's nothing moving on the.
Yeah, I can see like if you're 2-body system, when you rotate the branch cards away from resonant region, then it becomes closer to the bound state pole. If I think about the complex plane, and then you say a branch card get rotated away from real axis, away from resonances, but they become closer to the bound.
For this case, I don't think it's sort of for the bound state. The most deep bound is actually the state itself, and when you rotate, it's not going to make it bound deeper, right? It's still, if you look at the term here, the leading term here, the sharpest drop can happen is when this takes when this takes the maximally the negative magnitude of that, right? So depending on the angle you rotate, when for the bound states, it's just simply there is no rotation. That's when it drops the fast. And when you rotate this bound states, it's going to be fluctuate and make things a little bit less bound. Okay. The correction is going to be larger. And for the resonance, we also run a benchmark, and we see that this is where we really need the subleading terms. And the leading term is pretty much matching the things, but because of the oscillations, at a few points where the leading term is small, it can reveal what's happening in the next leading order terms. We have two resonance benchmark. This is a wide resonance, and this is a narrow resonance, and they both work really well. Okay, so for the future, the finite volume thing is really rigorous division, but we have done case by case. And we use this finite volume method to extract information from discrete levels, and we compare this. This is actually an exact method, but it also shares some similarities between the emulators as well. The emulator is a person-made method, but it still works in general. And the method to get the emulator work is first we train the feedable emulator with data, just similar to the finite volume method. We also feed the finite volume with data. And the worst thing about the downside of the emulators, I actually see the accuracy depending on how you feed the data with. And in our case, we want to consider a special case where the eigenvector continuation works. And this is a really nice emulators. And we are going to talk this preliminary idea about the finite volume and eigenvector continuation. There are previous works that trying to get the easy works in the finite volume. For example, The work by my colleagues, Nguyen, and my advisor, Sebastian Koenig, has this finite volume EC methods that is basically working on a DVR method, has a DVR method in mind. They keep the same DVR base, same number of DVR bases, and they just simply scale the they just simply scale these wave functions depending on the volume of the box. It is sort of equivalent to scale the potentials by the relative to the box size. And the benefit of this implementation is a lot easier to do because we can only just scale the wave functions and while we're keeping the same number of bases, it's just a rewrite of everything by a scale factors. And what is even better is when you do this on the lattice, which is DVR basis, you only need to scale the mass. And the problem for me is I'm trying to use, trying to relate it to lattice EFTs, which is hard to change the size, or they change the space between lattices, the lattice size. And also I need accuracy way better than the finite volume EC method. So what I'm planning to do is I'll take a deeper look at how the EC works. And in the initial paper, they sort of relate this concept to some mathematical eigenvector continuation. And the reason behind that is the EC vector is evolving slowly and compared to the Hamiltonian matrices. And these form a low-dimensional manifold of the vector space. And for the finite volume case, it's a little bit tricky because the finite volume conditions actually form a circle instead of just localized Euclidean space. And the way to solve this missed part is we can try to sampling the EC vectors evenly across the circle. Or maybe because we actually know what happens in the finite volume, we can just use these vectors together with the EC and form a new method that is I'm currently working on. The simple version of this is we have a parameter vectors that satisfy the boundary conditions, and we apply the eigenvector continuation with these vectors. And on this panel, we see two pictures about even though there's a huge change, there's nothing really changed in the interactive, in the parts that really matters for the interactions. The big change actually happens where the finite volume methods works. And in a simple 1D case, because we know this infinite shifted sum of the shifted sum of the infinite volume solutions actually works pretty nicely, we can use this L to parameter these these vectors, and this is going to be a really good solutions, just like the eigenvector continuations. And our method can extend to scattering states, although I have designed this method with bound states in mind, but it's a lot complicated and we need to use a technique similar to R matrices method. The major benefits of my implementation is compatible with lattice setup. So here is some result about bound states I benchmarked. As you can see, the subleading term in this panel, this is the two-body calculations. And you can see the subleading terms emerges here has been really taken care of by the EC method compared to the Lüscher's original prescriptions. And here is a toy setup where we have three particles interacting with each other, and there's no subleading terms. And this is a proof of concept, and just to showcase that it really works in the three-body bound states as well. For the scattering states, this is also a preliminary idea that we have a sampling points, 6 sampling points, one is hidden here. And we trying to train this our EC method with 6 sampling points and see how it performs on the scattering spectrum. And we found that it is not only extrapolates the scattering solutions well, it also extrapolates the bound state solutions relatively okay in the finite volume.
you emulate for each individual state or reaction, just emulate for all the states at once.
How do each emulate each independent? Because the lattice is changing.
So okay, so basically emulate each curve, right? So you have each curve.
The curve is emulated all at once. For example, we have a 20 here. I can get everything in the 20s. If I have 18s, I have all the 18s. So we just need to change the 18. Because we change the L, the lattice also needs to be changed. You can't just get all the from 18 to 20. You have to do each lattice size, each lattice volume every time. Okay, and as a summary, in this talk, I discussed how the finite volumes and how to derive finite volume methods, and in the presence of the long-range forces, and have some initial applications to nuclear reaction theories. And what happens, what's the challenge arises from these discussions is actually we need to understand better about the alpha cluster particles. And because of these challenges, we don't want to always to set up a finite volume calculations, theoretical derivations each time. I think it might be a good approach to actually using an emulator approach for all these different considerations. And yeah, this is my talk, and thank you for coming. And yeah. Thank you for the talk. There's a lot of topics. Any questions? Sure.
I have a rather mega technical question. So if you don't know the answer, don't worry, I will know it tomorrow. But is there a difference between the finite volume extrapolation with a continuation and what people in the reduced basis method literature call the reference point?
I would simply regard the, as my method I talked about, the finite volume with the eigenvector continuation as the subcategory of the reduced basis method. And because the eigenvector continuation is also a you can just simply regard that as a reduced basis method, and I don't think there is a major difference. It's just how you extract information from these methods. Does that answer your question?
So mine was more specific with the finite volume extrapolation part.
Yeah.
Not with EC and stuff.
Oh, not with EC, you mean?
Yeah.
Oh, okay. So the finite volume method, the reduced basis method is approximation, right? If you truncate basis wrong, you get wrong answer. But the finite volume, on the other hand, is the exact method. If it's if found something wrong, like those people doing the lattice QCDs, if you find your data isn't really working with the finite volume method, it's probably something that's unexpected in your calculation. Okay.
Okay, I will annoy you.
Okay.
This is a long short question. So in the coupling between experiment and theory, usually there's a problem that experimentalists measure quantities that can be interpreted theoretically, because they measure something that's fuzzy and there's no physics following out of that. There's no point measuring or analyzing data for that. And from the theoretical side, one can calculate things that experimentalists measure, and you can calculate it more accurately. And of course, that gives reason to experimentalists to measure something more accurately. You can also make it pure, more general, cover more things. But real progress is when you have more powerful theory, more powerful calculations, is that you can predict things that experimenters did not measure so far, and you give them the reason to measure it, look at nature in more ways. Do you have this kind of avenue? I mean, for example, you alluded to complicated structure in the data where you have different cluster structures interfering.
I'm not quite familiar with the experimental side. But as far as I know of, the NC calculation is just a calculation, to calculate NC, even if you calculate this data from experimental data, it's still a theoretical calculation because everything is in the experiment. It's hard to get things down to the astrophysical energy level, which things are pretty much they have low energies, and usually it only happens like in the scale of the universe when you have a large star, something like that. I don't really know if there are any experiments that can be done on this scale, but I would say that it's definitely we are working towards a scale where to help to help understand the experimental data we already collected.
Fundamentally, right, people here do ab initio is simulating nature. Is another approach.
Yeah.
Right, but the point is that you can, in experiment, you focus on this channel or that channel, this, that kind of final state. And if you give, I don't know, 3-bonded decay and you predict direct stuff for the 3-bonded decay.
Mm-hmm.
And you actually get some kind of understanding that if the 3-bonded direct flow moves this way and not that way, you answer some kind of question.
Well, yeah, I think in principle the lattice calculations have all those stationary waves in the simulation data. It's actually a matter of how you dig those information out on the top of all these finite volume corrections that change the system from nature. But I don't. It seems like you worry about very low energy astrophysics scales energies. Like you see, like what you say seems to suggest that it's very difficult in your calculations for very low energy reactions.
The difficulty in my calculations is basically just the problem. How to it's not low energy. It's the breakup or the separation energies is comparably low to the binding energies of the nuclei, binding energy of the large clusters like neon 20 and oxygen 16, which they have like hundreds of MeVs, compared to the separation of binding energies, which is only like a few MeVs. The errors are going to be significant here because they have like scale factor of 10 and 100. And that is how we can get accurately on this small difference, accurately represented in the data we have.
Oh, so you're saying the threshold again comes to the issue of threshold. You have very, very small threshold. It's very hard to get.
Yes, if you have really small structures, like like for example the billion the 2-hour clusters, the resonance, the even the most advanced ab initio technique is having a hard time trying to accurately capture that. Any other questions?
Sure.
Okay, so the second one, maybe the second one, you are talking about the complex scaling and said that it may have some potential to resolve some issues in your calculation without complex scaling, which relates to some cluster, right?
Yes. In the classic calculations, in the classic calculation, we only have like a few data points, right? Only like a couple, like 5, 6, depending on the accuracies and the energy levels. And there are subleading terms, there are other exponential terms that might be hidden. And because of breakup channels, we have lots of breakup channels, right, happening in the same time. Like if you extract the protons from a cluster, and you can also extract alpha particles from the clusters, and this is giving lots of different breakup channels. And if you have more data, you can certainly add these channels to the finite volume method, and the complex scaling. If we manage to make it work on the lattice, which I'm not sure how that goes, and you can use another parameter without changing the lattice setup, right? You just have to change the potential, the interaction of the lattice, which is going to be a challenging part. And that is going to give you more finite volume data compared to just simply varying the lattice size.
No questions? Yeah, actually, okay, so we're toward the end, so the census data. Yeah, again, like anyone wants to go to the